Hello, everyone. Great pleasure to be here today to talk to you about mitigating bias and privacy concerns in visual data. I'm Olga Russakovsky, and I'll be joined today by PhD students Angelina Wang, Vikram Ramaswamy, and Kayu Yang. In the past few years, there's been increased attention on the fact that computer vision systems exhibit a number of undesirable, potentially harmful behavior as they're deployed at scale in practical applications. So for example, computer vision models that learn to quote unquote increase attractiveness by manipulating skin color, or machines that are taught by photos learn a sexist view of women, or facial recognition is accurate, but only if you're a white guy. There is been a lot of very rich literature trying to understand the causes, the downstream impacts, the history behind these kinds of effects. And I'll point you to one work in particular by my colleague at Princeton, Professor Ruha Benjamin, in her book called Race After Technology, that does really a deep dive into some of the root causes, some of the impacts of these kinds of issues of sexist, racist technology. But in this talk, we'll actually look at a simpler view. So we'll just consider this simplified cycle where human history, bias, and prejudices are making their way into large-scale data that we're using to train our models. The models are then making some kind of decisions out in the real world, and this becomes part of our history. And so the question that we want to ask as computer vision engineers is, can we adjust the AI design to try to mitigate some of these effects? And so in this talk, we'll sort of focus on various parts of the cycle and talk through some of our efforts around measuring as well as mitigating some of these kinds of harmful effects. So let's start by taking a look quickly at the large-scale data. In the last few years, there's been a number of works pointing out the fact that large-scale data does not necessarily mean that there is fair representation within the data set. So there's been work, for example, including the seminal work by Joy Blamwini and Timnit Gebru, as well as some of our work in the past couple of years, as well as many others, pointing to the lack of demographic diversity in data sets. So even though a data set is large scale, that does not mean that people of all demographics are equally or fairly or appropriately represented in the data. There's been another very interesting line of work that I definitely want to flag around geographic diversity. And this demonstrates that in current large-scale visual recognition datasets, the images come from particular countries, particular continents, and many other places are entirely unseen in this data. So this suggests a couple of things. So first of all, even for something as seemingly innocuous as object detection, the models that we're training are representative of particular countries and not of others. So even for something like object detection, where you wouldn't think that fairness issues come into play, actually, if you look at the object detectors that are being trained from using ImageNet, using open images, you see that they only work for certain countries. Let me give you a concrete example. So if you train a model for recognizing soap, you may get something that actually recognizes US brands of liquid soap, rather than, for example, recognizing bar soap, which is the kind of soap that's used in the vast majority of countries. And so mostly this goes to show that fairness issues are not necessarily only applicable when our data set is around people. So even if you're working on something like object detection, these kinds of effects may very well be relevant to your research as well. And finally, I'll say that a lot of these issues of underrepresentation come from the fact that we're collecting these large-scale data from search engines. And there's known bias in image search engines, and I'll point you to. I mean, there's a lot of works in this space, but for example, a book called Algorithms of Oppression by Safiya Noble came out a few years ago, and it does a really nice deep dive into the kinds of biases that are embedded in search engines generally, and image search engines in particular, that may be relevant. And so with that in mind, I will pass it off to Angelina Wang to talk about a particular tool that we designed to try to reveal and mitigate biases in large-scale visual data. So given that we know these biases exist, the question is, which ones exist in which particular data set, what kind of biases are present in this data set, and how do we go about measuring and mitigating some of these?
Hi, I'm Angelina Wang, and I'm going to talk about work with Arvind Narayanan and Olga Russakovsky called Revise, a tool for bias mitigation. It takes in as input a visual data set and its annotations and outputs metrics, seeking to produce insights and possible actions. We aim to go beyond simply documenting underrepresentations, but also looking more deeply into how the portrayals of the image differ along various axes. We perform a number of automated analyses that take advantage of the rich visual images in the dataset. Due to the automated nature of our tool, we are able to surface discovered patterns on large-scale datasets at a level at which human inspection would be impractical. For example, in the Coco object dataset, we see that overall, men are featured more frequently with sports objects and in outdoor sports scenes, whereas women are featured more frequently with kitchen objects and in shopping and dining scenes. These kinds of high-level trends are not discernible at an individual image level, so automated analyses of the full dataset are required. However, while these portrayals are quite stereotypical and potentially very problematic, the concrete interventions that should be taken are ultimately very dependent on what the actual downstream task is the models trained on this dataset are going to be. Thus, this tool is intended to help dataset users diagnose what kinds of biases the datasets they are training their models on may contain, because these same biases may propagate into the model. Our tool is also intended to help dataset creators themselves, who can iteratively query the tool to find biases that may be present in their dataset and adjust their data collection or labeling process accordingly. Suggestions of how to counteract discovered biases are recommended, but ultimately it is up to the dataset creator to ascertain which biases are problematic, such as those that reinforce societal stereotypes, and which biases are more harmful. Our tool is available on GitHub as interactive Jupyter notebooks. Please check it out.
Thanks very much, Angelina. So using Revise, we can try to get a little bit of a better handle on what kind of biases are present in the data and try to take some steps towards mitigating them. But of course, the mitigation steps may not always all be possible, right? So the data may in fact reflect the kind of unfortunate realities of our world and the kind of stereotypes, the kind of biases that exist in the world right now. And so fixing the problems just at the data level may not be possible. So we turn our attention now to trying to mitigate the design of models to try to mitigate some of the harmful effects. There's very rich literature on designing, analyzing, evaluating fair models, and I can't possibly hope to do it justice here. Point you to work by Ben Hutchinson and Margaret Mitchell from a few years ago that presents 50 years of history of ML fairness research. That's a great read. There's a number of works around model design. For example, sort of point you to one by Tse Wang out of our lab last year at CVPR 2020. There's a lot of literature on interpretability, trying to get an understanding of sort of what kind of patterns the models have learned, and in that way sort of take steps towards mitigating these biases once we understand what is being learned. A number of works similar to interpretability on analysis of models. Again, I'll sort of do a plug here for work by Dora Zhao as well as Angelina and me that just came out on arXiv a couple of days ago, studying racial bias in image captioning, sort of doing an analysis of those systems. And then finally, a number of evaluation metrics have been designed, right? One question is, what does it mean to have a fair model? And again, very rich literature in this space. I'll point you to, of course, one in particular from our lab. This is by Angelina and myself that is published in ICML this year around introducing a new metric for bias amplification. And so I'll point you to all of these papers sort of to read more. But now we'll talk about two particular projects in the space of sort of building more quote unquote fair models. And so the first project, I'll pass it off to Vikram Ramaswamy to introduce. We're trying to enable training fair models according to various fairness metrics from imperfect data. So we're saying, assuming we have a data set that has known biases. So for example, gender, for example, women occur more often with a particular object or doing a particular task. And we're trying to train a gender neutral model for recognizing this task. So I'll pass it off to Vikram to do a deep dive into this work.
Hi, everyone. I'm Vikram, and today I'm going to talk about our work for attribute classification through latent space debiasing. This is joint work with Sunny Kim and Olga Russakovsky. In current data sets, certain attributes like gender tend to be correlated with certain tasks like cooking or coding. Let's say we want to train a hat classifier, and suppose wearing hats is correlated with a gender. Then the classifier might pick up on gender cues rather than hat cues. Or similarly, suppose wearing hats is correlated with wearing glasses, as shown here. This classifier might only recognize hats in the presence of glasses. What we want, ideally, is a dataset wherein these two attributes are independent. However, it is hard to collect huge amounts of data from the real world that's unbiased. One possible workaround is to use GANs to create a synthetic dataset instead and augment our real images with these synthetic images. As a quick overview, here's how we can use GANs to augment our data. We can sample random vectors z in the latent space and use the generator to get an image for each latent vector. We can then hallucinate labels for the synthetic images using a model trained on just the real data. Now, with both the real images and the synthetic images, we can train a target attribute classifier. An interesting observation made by Denton et al. Was that the latent space of a GAN is quite structured, and in fact, most semantic attributes are approximately linearly separable in the latent space. This is our first idea. Using a linear SVM classifier, we can learn the hyperplane for glasses as shown in the image. Now, given a latent vector z, we can compute a vector z prime that flips the glasses score. This allows us to compute pairs of images, one with glasses and one without. The main issue with this, however, is that we have no control on whether or not the image generated from z prime has a hat. In fact, naively perturbing the images in this way can maintain biases. For example, when we add glasses, we also add a hat, as shown in the image. Since we want to control both the hat attribute as well as the glasses attribute, we can compute hyperplanes for both of these. Given these hyperplanes, we can then compute a hat score and a glasses score for every latent vector z. We can then compute a corresponding z prime that has the negative of the glasses score but the same hat score. The intuition here is that both z and z prime are either wearing hats or not wearing hats, and exactly one of them is wearing glasses. Computing our balanced synthetic dataset in this way has many advantages. The first one is that our method can use a single GAN to decorrelate multiple predicted target attribute pairs, whereas previous works require one GAN per attribute pair. This method also preserves the intra-class variation of the attribute. Consider an attribute like smiling. This attribute ranges from not smiling to partially smiling to smiling. Since the z's are chosen at random, a similar distribution exists in the synthetic dataset. The final advantage is that the samples are generated to maintain independence between the target and the predictor attributes. We'd like to understand how well training with a synthetic balanced dataset would do. To do so, we use a Celebi dataset and train attribute classifiers for 26 different target attributes on both real and synthetic data. Since we care about fair classification with respect to gender expression, we measure the performance of our model using 4 different metrics. The first metric, average precision, is a threshold invariant accuracy metric. We also measure 3 other fairness metrics: difference in equality of opportunity, bias amplification, which is the method that Olga just mentioned, and the KL divergence between score distributions. We find that training with such a balanced data set suffers a small loss in average precision, but performs better on all 3 fairness metrics. Our paper includes other results such as ablation studies of other perturbations, analysis of when our method performs well, and comparisons to prior work. To conclude, we find that our proposed method is effective in reducing bias in visual attribute classifiers. One current limitation is that this work just decorrelates 2 or maybe 3 attributes. It's possible that while doing this decorrelation, we are adding bias along yet another attribute. For future work, this is something we can try to measure and eliminate. As a more long-term goal, we'd like to extend this method to a more complicated data set like COCO. If you're interested in this work, here are a few links with more information. Thank you.
Thanks so much, Vikram. So we've talked so far about training fair models, right, given imperfect data. So let's ask a different question now. What happens when you have a data set that is good for training the kind of models you want to train, that sort of works well for the task that it was collected for, but that has some kind of issue? So for example, that has a privacy concern where there are people included in the data set that may not have consented to being in the data set and whose privacy may be violated by virtue of being in the data set. So how do we go about solving that problem? I'll pass it off to Kaiyu to introduce that work.
Hi, this is Kaiyu Yang presenting our work on face obfuscation in ImageNet. This is a joint work with Jack Liu, Feifei Li, Jia Deng, and Olga Russakovsky. Large-scale datasets such as ImageNet drive the recent progress in computer vision, but at the same time, they also pose privacy threats to people in the images. There are only 3 categories among the 1,000 categories in the ImageNet challenge dataset. However, there are many incidental people in the images. For example, these images are from barber chair, husky, beer bottle, and volleyball, none of which are people categories. In this work, we attempt to mitigate the privacy issue. First, we annotate human faces in the dataset, facilitating subsequent research on privacy protection. Second, we show that face obfuscation does not hurt both image classification and transfer learning using ImageNet. We annotate face bounding boxes on 1.4 million images in the ImageNet challenge dataset. 243,000 of them have at least one face, which is about 17% of all images. There are 563,000 faces in total. Then we obfuscate the faces using 2 simple methods, blurring and overlaying. The obfuscated versions of ImageNet better protects privacy, but are they still useful? A major use case of ImageNet is as a classification benchmark. We benchmark multiple deep neural networks separately using original images, blurred images, and overlaid images. After face obfuscation, the validation accuracy drops less than 1%, demonstrating that we can train privacy-aware visual classifiers on ImageNet and remain competitive accuracies. Besides a classification benchmark, ImageNet also serves as the pre-training data for transferring to other domains. Here we train models on different versions of ImageNet and fine-tune them on 4 downstream tasks: object recognition on CIFAR-10, scene recognition on SOUND, object detection on Pascal VOC, and face attribute classification on CLAB-A. On all tasks, models pre-trained on obfuscated images achieve competitive performance. In summary, our experiments show that face obfuscation does not significantly compromise performance. Therefore, it should be included in both ImageNet and future dataset creation efforts.
So thanks so much, Caillou. Also point out, so Caillou Yang is about to graduate with his PhD, will be on the academic job market shortly, so please be on the lookout. So far in the talk, we've covered large-scale data and AI models and talked about interventions in those parts of the cycle. But there's one last bit here, which is the fact that these AI systems are being deployed in the real world, and there are people who are making very impactful decisions about where the data should come from, how the AI model should be designed, how they should be deployed, what applications should be tackled. And if we are trying to have a conversation about building fair AI systems, we can't hope to have this conversation without addressing the kind of bias that comes from AI researchers. And in particular, right now, the field of AI, as I'm sure you know, is fairly homogeneous. There is definitely a lack of diversity and a lack of representation, a lack of inclusion, particularly among AI leadership. And so just in the last few minutes here, I want to talk about some of our effort to try to increase diversity and inclusion among AI leadership so that we actually have some hope of building fair and inclusive AI technology. So AI for All is a nonprofit dedicated to increasing diversity and inclusion in AI. So I co-founded it a few years ago together with Fei-Fei Li, who I hope you're all familiar with, as well as Rick Sommer, who is an expert in K-12 education. So at AI for All, we say that AI will change the world. It is already changing the world, and we ask the question of who will change AI. And so our goal is to educate and support a diverse next generation of AI leaders. To do so, we partner with a number of schools and universities and companies and design educational programs for students from demographics who are traditionally not represented in the AI field. We try to show them a path within AI. We try to excite them about the potential about this technology, give them some of the tools they need to get started in the field. And then we run Changemakers in AI, which is our alumni community run by the national nonprofit, by AI for All. And so within Changemakers in AI, these students are provided with ongoing educational opportunities and mentorship and community and leadership opportunities for as long as they choose to stay within AI. My all-time favorite quote is, until this program, I never thought that people who look like me could succeed in computer science and AI. This is from an AI for All 2016 student, and this is why we do what we do. So with that, I'd like to conclude. So we've talked about this cycle of AI bias propagation and touched upon kind of 4 different projects within this space, so 3 research papers as well as our work at AI for All. I'd like to give a big thanks to all of the students, of course, especially Angelina, Caillou, and Vikram, who we met today, as well as many others in the lab who contributed to this work. Please visit us, visualai.princeton.edu, as well as aiforall.org. Thank you.